Okay, this is going to be our fifth video in the rotational motion series here. And in this video, we're going to take a look at angular momentum and its conservation. So once we've sort of defined angular momentum and taken a look at the conservation of angular momentum, we're going to be in a good position to answer questions like, why does the Earth continue to spin, or why is it that a figure skater will spin more quickly as they pull their arms and legs in toward their axis of rotation, okay? And so we're going to take a look at that, but as I mentioned first, before we can really talk about the conservation of angular momentum, we need to define angular momentum. We're going to give angular momentum this symbol L, okay, capital L. And we define it as we have here in equation 1 where it's boxed off. So L is equal to I omega, where I, again, like in previous videos, I is our moment of inertia, and omega is our angular velocity. Okay, and so we can see, like many of our previous sort of rotational expressions, the angular momentum looks very much like the similar equation in linear terms, right? It looks like our linear momentum definition, which we have over here. Our linear momentum was equal to mass times velocity, where our angular momentum is equal to the moment of inertia, which often replaces our mass term when we're going from linear to rotational, and our velocity is replaced by angular velocity again, which is the similar rotation that we see when we go from, or the similar replacement, I should say, that we see when we go from linear to rotational, right? And so I'll just note here that the SI units for angular momentum are kilogram meters squared per second, and whenever we need to transfer between units, we'll go back to kilogram meters squared per second. Okay. And so we're going to start off working with this equation by doing a simple example here. I think I have the numbers directly from the text. Yeah, I'm going to be copying these numbers directly out of the textbook. And so let's take a look at what we have here. Okay, so we want to calculate the angular momentum of the Earth. Okay, and so how are we going to do that? Well, we can start off. We know that our expression for angular momentum is this right here, right? And what's the Earth? Well, the Earth is basically a sphere, right? So we need the moment of inertia of a sphere, and this is a full sphere. This is not like the shell of a sphere. This is a full solid sphere. If we look that up in the table that I showed a few videos back, or in the textbook, we're going to find that is this moment of inertia is given by 2mr squared over 5. And so what are we going to need? We're going to need to know the mass of the Earth and the radius of the Earth, right? And so these values are given to me in the textbook, but you could look them up anywhere. We have a mass for the Earth equal to 5.979 times 10 to the 24 kilograms, and a radius of 6.376 times 10 to the 6 meters. Okay, and of course we know that the Earth's angular velocity is going to be 1 revolution per day, right? But we want to convert this 1 revolution per day, so this will be 1 rev per day. But we want to convert this 1 revolution per day into radians per second, right? So we'll kind of do that as we go. Let me rewrite our equation here. So we have L, which is going to be equal to, well, if we divide 2 by 5, so let's say we have 2/5, so I'll just pull that out on its own. Then we're going to have our mass. We're going to have our radius. And we're going to have our omega here, but we know it's 1 revolution per day, right? So that's just going to be a 1, and we're going to make the conversion here in a moment, but before we do that, so if we multiplied all this out, we would end up finding 9.72 times 10 to the 37 kilogram meters squared, but it's not per second, it's revolutions per day. Okay, but we don't want revolutions per day, so what we need to do is we need to multiply by 2 pi radians per revolution, and then we need to divide by how many seconds per day there are, right? So we need to take this result, we need to multiply it by 2 pi, and this is rads per rev, so radians per revolution, and we need to divide that by, and the book tells us 8.64 times 10 to the 4 seconds per day. So that's how many seconds there are in a day, right? If we do that calculation, we're going to end up getting that L is equal to 7.07 times 10 to the 33 kilogram meters squared per second. Okay, and so that is the angular momentum of the Earth. We can put a box around that. That's our final answer for that question. And so that's how we can make use of the angular momentum formula. Okay, so that just gives us a sort of quick look at how we could find values for different angular momentums if we needed to. Okay, now if we think back, we can think back to our discussions on linear momentum, and if we remember, we kind of went right from talking about linear momentum, and then we talked about this change in momentum, delta p, which we called the impulse, right? I haven't written it here, but you can remember that we defined delta p equals f delta t. This was our impulse, right? So a natural question would be, after thinking about this for a while, well, is there a sort of equivalent to this impulse idea in terms of angular momentum? And it turns out that there is. And the textbook does a really particularly good job of writing this part up. I really like it. It's a very concise couple of paragraphs here, and they get to the point. So I've just copied it directly from the textbook, and I'll read it out to you guys. So I quote from the textbook: "When you push a merry-go-round, spin a bike wheel, or open a door, you exert a torque. If the torque you exert is greater than the opposing torques, then the rotation accelerates, and angular momentum increases. The greater the net torque, the more rapid the increase in your angular momentum. The relationship between torque and angular momentum is shown right here, right? So we have net torque is equal to the change in angular momentum over the change in time, right? And so this expression is exactly analogous to the relationship between force and linear momentum, which I just talked about, right? So this equation that we see here is our impulse equation, just slightly rearranged, right? So we've moved the delta t from being next to the f, and we just divided through by it, right? And so this is basically exactly the same equation, but in rotational terms that we're looking at now for the change in angular momentum, right? And it turns out this is a very widely sort of applicable tool, and we're going to take a look at a number of other uses from it, and we're actually going to see that this equation leads us to conservation of angular momentum here just in the next page here. But before that, let's take a look at an example. So this is an example like the one from the textbook, but I've modified it slightly just to give you guys some different numbers to look at. You can take a look at the one in the textbook if you want to see a second example. But so in this example, we're taking a look at an upside down bike tire. We've looked at this a couple of times before. So this upside down bike tire is being spun by a person, right? So we have like a bike tire here, let's say, and somebody is spinning it. They're applying a force to it like this, right? So the person exerts a force of 10 newtons perpendicular to the radius of the tire, as I said there. So it's perpendicular. We're given the radius, and we're given the time over which this force is exerted on the tire, right? So the person's always exerting this force perpendicular to that radius. So in part A, we want to find that if we assume negligible friction and that the tire starts from rest, we want to find what the final angular momentum of the tire is going to be, right? And so how do we get to that? Well, we just talked about this equation, right? We just talked about tau is equal to delta L over delta T, so it seems logical we'd probably want to start from there. We can rearrange this to get delta L is equal to tau times delta T, right? And now if we split up our delta L, we know that delta L is just L final minus L initial, and this is going to be equal to tau delta T, right? We could break up the delta T also. I mean, maybe I'll do that. It'll be time final minus time initial, right? And so let's just set our, well, we're told that our initial angular velocity is 0, so this is going to be set to 0, and we can just set the time that we start the experiment to 0. And if I just drop these f subscripts, that's going to leave us with an equation that looks like this. So we're going to have L equals tau t, okay? Except that we know we can rewrite tau as rf sine theta, right? But in this case, our sine theta is just going to be 1 because we're always, our force is always being applied at a right angle to our radius. And so if we make that replacement, this is going to give us L equals Rf t, right? And at this point, we are ready to solve the problem, right? I'll sub in numbers down here where we have L equals Rf t. We're told that the radius of the tire is 0.3 meters. We're told that the force applied is 10 newtons. We're told that the force is applied for 0.2 seconds, right? And if we do that calculation, this is going to tell us that L is equal to 0.6 kilogram meters squared per second, okay? So that is our answer for the angular momentum of that tire after that force has been applied for 2 seconds, okay? In part 2, or in part B I should say, part B, what are we looking for? What's the final angular velocity of the tire given that it has a mass of 2 kilograms and assuming that its moment of inertia is that of a hoop, okay? Okay, so what are we told? Well, we're told that we have a mass of 2 kilograms. We still have that radius of 0.3 meters. We know that from our definition of angular momentum, we know that L is equal to I omega. We're looking for omega, so it seems logical that we should probably isolate omega and try to find these other terms. We just calculated L, so we're fine there, but we need an I. We can look up I, so for a hoop rotating about its cylindrical axis, we can look that up in the table, and we're told that it's equal to mr squared. But in this case, m is just our mass and r is just our radius, so that's basically just mr squared for the values I've written down over here. And again, we're at the point where we can just substitute in numbers, right? So we have omega is equal to 0.6 over our value for I, which is our mass, 2 times 0.3 squared, right? And if we do that calculation, we're going to find that omega equal to 3.3 radians per second, okay? So the tire starts off from rest. We apply that force for 0.2 seconds. When we're done, the tire has this angular momentum, and it has this angular velocity. Okay, and those are the two answers for those questions, the questions in part A and B. Okay, and so we're kind of getting to where we want to here with this section. We can now looking back. Let's say we look back at this expression that we have here. Maybe it's not immediately obvious, but if we think about it for a second, what we really have here is another conservation law, right? Because we have that the net torque is equal to the change in our angular momentum over the change in time. But if we have no net torque, then angular momentum can't change, right? Even if time is changing, if this side is equal to 0, then our change in angular momentum has to be equal to 0, right? So we have a conservation law here. Angular momentum can't change if there's no applied torque. And this is basically what I'm talking about here. So we say that with no external torque being applied to the system, so a tau net equal to 0, we have no change in our angular momentum, right? So our delta L is equal to 0, and that means that our L has to be constant, right? And so this conservation of angular momentum is just another sort of conservation law that we can use to solve a lot of interesting problems. It's a very powerful tool, just like conservation of energy and conservation of linear momentum were powerful tools. So is conservation of angular momentum. And this kind of answers the first part of the question that we set up in the sort of intro to this video here. Why does the Earth continue to spin? Like, why is the Earth always spinning? Well, it's spinning because there's nothing to stop it from spinning, right? There's no torque being applied that would stop it quickly enough that we would sort of notice, right? So the Earth is sort of very slowly spinning down, and if you're interested, the textbook does go into a little bit of detail on how much slower the Earth is rotating now than it did several 100 million years ago, I believe. But basically, the answer to the question, why is the Earth still spinning, is that there is no net torque being applied to it that we would notice the slowdown. Okay, I mean, we can notice it if we look at it very carefully in scientific studies, but on a sort of human time scale, we're never going to notice the slowdown, right? And we had a second question that we had set up in the beginning of the video, which was, why is it that an ice skater will spin more and more rapidly as they pull their sort of body parts, like their arms and legs, inward toward their center of rotation? So why does that happen? Well, we're going to explore that in this last example for this video, and this should give us our answer. Okay, so I think I have numbers. I do. Okay, so here we have, so suppose we have an ice skater that is spinning at 0.8 revolutions per second with her arms extended, so sort of standing in like a T kind of position with her arms out. And suppose that her moment of inertia in that position is 2.34. This should be kilograms, not kilometers. So kilogram meters squared with her arms extended, and then with her arms pulled in when she like tightens up to be super straight. Her arms are tucked in by her side, and so are her legs. It'll go to 0.363 kilogram meters squared. Okay. And so we want to answer the following questions. What is her angular velocity in revolutions per second after she pulls her arms in? And then, well, I'll read part B when we get to it. Okay, so for part A, what are we doing here? Well, we know that nothing is really happening here. She starts off and all she's doing is pulling her arms and legs in. So there's no external torques, right? She's not doing anything additional to give herself an additional torque. So tau net is going to be equal to 0. But we just talked about that because, well, maybe I'll write it here. We know that the tau net is equal to delta L over delta T, and then this means that delta L must be equal to 0, right? Because tau net is equal to 0. And so if that's the case, then this means that L has to be a constant, right? L cannot be changing. And so if L is constant, then we can kind of write down that L is going to be equal to L prime, where L is our initial angular momentum, and L prime is our final angular momentum. So this initial one would be when the skater is spinning with arms out and legs out, and this final one would be when the skater has pulled in arms and legs and is now spinning sort of in as tight of a configuration as she can be, right? Super tight arms in, legs in. Okay, but we can rewrite both of these terms because we know that L is equal to I omega, right? So our moment of inertia times our angular velocity. So we can rewrite things like this, and these primes again indicate after everything has been pulled in, right? And so I will change, right? We know that depending on the configuration in which she's standing, her I will be different. Her moment of inertia will change, and because of that, her omega will also change, right? Because both of these sides of these equations have to balance. It has to be equal all the time. It has to be true that if I is decreasing, oops, that's not decreasing. If I is decreasing, then omega has to be increasing, right? And we're going to see that that's the case. So what are we looking for here? We are looking for omega prime. So let's solve for omega prime. Omega prime is going to end up being equal to omega times I over I prime. And what is that? Well, we can substitute in numbers. We have 0.8. We have 2.34 over 0.363. Okay, and if we do that calculation, we're going to find that omega prime is equal to 5.16 revolutions per second. Okay, so be careful here. We are in revolutions per second because we started off with our initial omega in revolutions per second, right? So we're still in revolutions per second, and that's fine if we're looking for revolutions per second. We didn't change from revolutions per second. We didn't try to go into joules or some other thing, calculating other values, which we are going to here in Part B, so we are going to need to change units. But if we were looking for revolutions per second, that's fine. If we were looking for radians per second, we'd have to be careful and switch to radians per second now, right? In Part B, though, we want to know what her rotational kinetic energy before and after she sort of tightens up her spin are, okay? And to be able to do this, we are going to want to go to radians per second because our rotational kinetic energy is going to be written in terms of joules, and joules have a built-in sort of SI requirement to them. They're written in terms of base SI units, and so we can't use revolutions per second to feed into our values, right? We have to go to radians per second. So let's take a look at this. Let's remember that our kinetic energy of rotation is equal to 1/2 I omega squared. Very similar to our translational kinetic energy, right? Just with our rotational variables. And so we can sub in for these right away. And I'm going to kind of do this all in one step here, right? So we're going to have 1/2. We're told that her initial I, her initial moment of inertia is 2.34 kilogram meter squared, but we won't need the units here. And I'm just going to put a larger bracket here. We're told that initially she's rotating at 0.8 revolutions per second, right? But how many radians per second is that? Well, there's 2 pi radians in one revolution, so we need to multiply this by 2 pi to get from revolutions per second to radians per second. And I'm going to close this off. And then remember, we're squaring omega here, so we're going to square the whole thing. We need this extra bracket here because we're not just squaring the 2 pi, we're also squaring this initial value because this whole thing is what gives us our omega in terms of radians per second, okay? And if you do this calculation, you will find that initially she had 29.6 joules of rotational kinetic energy when she was initially rotating with her arms out and stuff, right? Now we want to know what her rotational kinetic energy is after she pulls her arms in. So we're going to look for Ke sub r prime. Same equation here. Again, we have 1/2 I omega squared, but this is going to be I prime and omega prime now, right? And so we can sub in numbers. We have all these numbers. We're told that this is 0.363. And we just calculated what omega prime was. That was 5.16. And again, we're in revolutions per second. We don't want to be in revolutions per second. We want to be in radians per second. And so this 2 pi brings us from revolutions per second into radians per second. Square the whole thing. Well, the whole thing, these two terms, the two terms that make up our final angular velocity. And if we do that and do the calculation, we find 191 joules of rotational kinetic energy. So she gains a bunch of kinetic energy as she's pulling her arms in. So a good question might be, well, where is this rotational kinetic energy coming from, right? We can't get energy for nothing. And we may have a question like this on the assignment here, so I won't totally ruin it, but you can imagine that it takes some energy for her to actually pull her limbs inward as she's rotating, right? Like the tendency is for her arms to want to stay as far out to the side as possible as she rotates, and as she fights against that and pulls her arms in, well, she's loading kinetic energy into the system here, right? And we can do calculations along those lines, but I'll leave that for the assignment, and I'll leave this here for now. I'll see you guys in the next one.